Welcome everybody. This is the lecture number 4 of the Artificial Intelligence course. In this session, we are going to talk about the agents that can solve a problem. In the last class, we have actually seen that any agent that is a goal-based agent that he can only solve the problem, because if it is not goal-based, then he would not be able to solve the problem. However, other things he can also consider, and then he can be better. But if any agent is not goal-based, then he would be not able to solve the particular problem. In the last class, we have seen that there was a problem that there was some agent. I'm not sure about this, that who this agent was. Let's say we are thinking that in terms of the person. So he was in some place called Arad, and he had to reach to Bucharest. So so he was some place A. He have to reach to the Bucharest, and he have to find out the right place. So last class we have seen that there was some this kind of problem was there. Okay. So we have seen that in this particular setting, the person who was actually traveling wanted to travel. He always knows that where he is. So what is around him, what is his location. That's why this particular agent environment of that particular agent was observable. It was discrete because he was either into this state or in another state, something like that. In between, we are not considering that what is happening in between. Known, he was knowing that what is the map. Deterministic, because if he goes from A and goes in this particular direction, he may be reaching some location. So it was fixed. It was not like that he when he start from A and goes take some action, two things are possible. It was not like that. Only one thing was possible. So this is the environment in which he was working. So we actually understood in the last class that if agent want to solve this particular problem, that how to reach from location A to location B, he have to tell that what are the sequence of actions. Okay, so he have to specify that what are the sequence of actions. If he specifies this, that for example, in sequence of actions we have talked about that go from this room to this room and this room to this room, something like that. If he does all these things, then he would be able to reach to the B. So going from, for example, go from A, go to B, go to C, go to D, something like that. He one by one he execute these things, so that his state changes, and at the end he reaches to the Bucharest. So in the general idea that we actually have tried to develop in the last class was this, that there is some state space, and on this state space person have to find out the problem, find out the solution. And this finding out the solution, we typically call it, we give it a name called search, that he is going to search to find out that what to be done. So what is the efficient way of doing search actually is the subject matter of this particular course. So so we are going to see various method today itself. So there are 5 components. Using them, he can understand that what is happening with him. For example, in Arad gives him the understanding that whether he is in Arad. So similarly, any other place he can tell. If it returns true, then he is into this particular place or not. Go tells that change the state from here to there. So if it is a consecutive state, just it is connected, then he can go. Otherwise, he cannot fly. Okay. Results, you can find out that if the two things are we combine, that he is in Arad, go to Zarind, then he reaches to Zarind. If there is a path, this particular function try to find out that if there is a path. Otherwise, this answer could be in Arad also if there is no path. Goal test, how to find out that whether he have done or not. So it is in Bucharest. If he tests that whether he is in Bucharest, because Bucharest was the final.
कंटेंट
Yeah.
है ना, so इथे ईमेल एड्रेस हे काय actually go to but
Narsing, Narsinger, are you asking a question? Narsing Rao, are you asking a question? Otherwise, please, I request you to mute yourself. Okay.
हे काय त्या पॅरामीटर हा तिथे काय दिलं ते sites TNS test okay site assets update
Narsimha,
keep finding HTML इथे browse करा browse आता ह्या NGB filing.html मध्ये
Sir, you can
काय
mute
होते
him.
बघा
Narasimha, please mute yourself. Thank you very much. Okay, so what I was telling that if you want to find out that whether you are into the final state or not, there is another function that you can use. Pathcast is very important. That whenever you are going to something, you want to do it efficiently. And to
Statistics.
if I go to the extreme,
Update engine manager.
one
There are
minute.
open and download with and open in a HTML text.
Narasimha
And
Rao,
go to
I would
folder.
take you out.
Sir, I think you can mute him.
Open
So I'm trying to find
and
out that
choose
people
and
Narasimha
notepad.
one
Notepad.
sim and
Okay.
or
Defect
Narasimha, please don't
to
do this.
You can right click and mute, sir.
defect
Right click on Narasimha and mute.
restore go to
Sir, you would also have a mute
Sir, you
all
are admin,
option.
so you can mute. Yes, sir.
Yeah. So yes, thank you. So pathcast is also important thing. And if I go to very extreme, I can tell that I can solve all the problem into the world. Okay, given 1 crore years. Okay, who is going to ask me? Okay, so that's why cast is very important. Cast should be reasonable. Then only we can tell that it is going to be happening. It is happening or not. Okay. So cost must be reasonable. Otherwise, I can ask the cost that is actually not logical. Then based on that, I can tell that I can solve every problem. For example, if somebody says that cost is to bring the moon on the earth, so I say that if you can bring moon on the earth, then I can write this thing or I can do something. So since the P is false, you know that any expression that is of this particular kind, that if give me this thing, I am going to solve this particular problem. If the P part is false, then this statement is always going to be true. That's not a good idea. Okay, so paths must be reasonable. Now, in the last class also, we have discussed this particular algorithm where I was telling that how the agent solve the problem. What is the overall way? So the first way was this, that you here a simple problem solving. So we have seen this. If there is a simple problem solving agent, it receives some percept that what is happening into the environment, and based on this it tells that what action to be taken. This is what we have to do, that because goal based system, a goal based agent has a understanding of the environment, then he sees that what is right now status of the environment is, and based on that is proposes an action to you. How it does? So here is an algorithm. The algorithm says that that he received the percept and state that what is the current state. State is actually known to him, and based on this, it understand that what is my current state. If sequence is empty, sequence is something that what actions I have to take one by one, and after that my things are going to complete. And sequence is definitely empty because you don't have any thing to anything specified, so you have to discover this. So this if statement says that formulate the goal, means what is the, somehow you define that what is the how you, what is the characteristic of this particular goal. Then formulate the problem, means you discover, formulate problem means you develop the state space of that particular problem, and by this you get the problem and you get the goal, and then you search for this particular problem. Search is an important algorithm, and we are going to see that the different way of doing search. Okay, on this problem you apply the search. When you apply the search, you get the sequence, and this is what the sequence is. The sequence of action that you have to take. This is what the sequence is. Okay. So when you get this sequence, so your task should be that you first get the first item. What I have to do right now. Okay, if you know that what these things I have to do, so you focus on the first thing that I have to do. These actions I have to take. Then what is the first action? So you focus on the first action only, and you say that this is what the action I have to take, and this action you are going to reply, and by this you are going to reply this particular thing. A very interesting thing is this, that in this particular kind of arrangement, after doing this thing, these things are remained that you have to do this thing. It may be required in some cases that you can follow some of the things, and or you do the planning after some time, or it may also be possible that if everything is changing very dynamically, then you can say that I have taken this action that, but I'm not going to follow these sequences. I would actually again reformulate when the second item after taking this action, I would again reformulate the problem and do the same thing once again. So one good example could be that, for example, the game of chess. Okay, consider the game of chess. So you are on some board position and you have to advance your move. So you find out that looks like that in this way, if you go, you are going to win. Okay, but if when you take this particular, so but you can only go for the first thing, and then the opponent is going to take the next move. So you cannot follow this particular strategy as it is. So it also depends that how the environment reacts with your actions. So next time you cannot follow this thing again, you have to formulate the problem and try to find out how to win, and then use the second one. So my precise point is this, that the second move you cannot go ahead. Second move again may have, you may need to reformulate the problem and go ahead on that. Okay, so please feel free to interrupt me if you have any questions. Okay, I just wanted to see the chat. Okay. ST Ritu has written something. Okay. There way to reach the. Please share the meeting link. Okay. Three way to reach. Okay. So hope everything is clear. Okay. Yes or no?
Sir, I had a question. Harshal here.
Please, 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 please.
Sir, just like you were explaining the kind of graph algorithm when we were like going from one place to other place, I think it is similar to searching a graph or like A star search. Is it this or something else?
Actually, you are perfectly correct. So when I'm telling the finding out the problem, so a few I think we started this thing in the last class itself, that we wanted to formulate the problem. The problem formulation part involves is a way in which we actually create a graph, that how the things are related, and then
Okay.
finding out the solution is only remained that if you are here, how can you reach to this particular place. Okay, so these things are going to come into the more details today. A star search is definitely a good idea, and we are going to see others also in this particular class. Yeah, you
Okay.
are correct.
Okay, sir. Yeah.
Okay.
Thank you.
So this is the problem solving agent. This is the problem solving agent that my problem solving is. This is the problem that my problem solving agent is solving. So this is the map that was actually deliberately not shown so that you can focus on the concept, and now you can think of the same thing, that the question that you are actually asking, that whether it is a graph on which we have to find out some kind of algorithm, some kind of things to do something. Okay. So somebody is raising hand. Please ask the question if you have. Harshal.
Sir.
No
Yeah,
question.
sir. I've just asked. Yeah. Yeah, it's
Okay.
Rudhani.
Thank you. Thank you. Okay. So sorry, I may not be able to. Yeah. Any question? Yeah.
Yeah,
Somebody else?
Rudra, I had a small question. Like in
Please,
the
please.
previous case, when we are talking of the sequence of steps we need to take, like we are formulating the problem and we are generating the sequence after the search function,
Okay.
if we say, right? So what I think this particular sequence, I mean, this particular solution works on is in a deterministic and fully observable system. I mean, am I completely wrong in this particular point?
No, no, no. You are completely. You are right. Yeah.
Okay. Okay.
Yeah.
So the
So
next.
look there,
Uh,
look there.
uh,
If your question is, if you are you wanted to ask this, let me formulate your question. You actually wanted to ask that if we have a graph, then we can solve this problem into this particular way, that finding out in some way, some searching method. Today we are going to see some of the method in detail. But I think your question is that if what if that if from this particular place, if I take some action, I may go here also and here also. Okay. In those kind of scenarios, when my system is non-deterministic, in those cases, if I take the action, I may not be really reach to this particular place. Okay, this is what the problem is. So in those cases, what I would do, whether this kind of thing would work or not. Are you asking this question?
yes,
Finding
sir,
out the
because yes, sir, exactly.
yes.
Because in the chess
Okay,
example, right?
okay. Hold on. So what would
Okay.
happen? What would happen in those scenarios? How to model this solution becomes different. Okay, right now we are modeling the things into this way, that because understanding of this particular way is easy. That's why we are telling. So then we have to go to the other kind of model, and those kind of models could be that probabilistic modeling. And you know that there was something called I just missed the name. So there are different kind of modeling which says that, for example, if you want to go from place A to B, and every time whenever you go to a particular crossing, you take random walk. The name is the random walk. Okay, random walk. So you just search on the internet that what is random walk. So those kind of different kind of modeling come into the picture, and they also can go and find out the search and what is the probability, what is the time to reach to this particular destination. Okay, so when the time when
Sir,
this thing would be,
Chandramoli here.
we would
Sorry for
discuss
disturbance.
this into more detail. Yeah, please. Okay, go ahead.
Sir, actually, I have one doubt. Now, I have three routes to reach Arat to Bokarat, right? Three ways to
Hmm,
reach it.
hmm, hmm.
So now the distance will be the different. I mean, kilometers, distance, and other things are different. How the agent
Yes.
can decide which one is the efficient? So first I have decided which is the efficient. Then I'll make a sequence of steps so I can reach it. Bokarat to 2 hours or 3 hours kind of thing. How the agent is
Excellent question,
deciding
because
on that?
yeah,
That is
excellent question. So right now we are not actually answering that thing, but ultimately our objective would be this, to solve a particular problem using efficiency. That's why
efficiency.
we are
Correct,
telling the
exactly.
path cast. This particular
Okay,
part is also
okay.
part of our system. That
Mm-hmm.
apart from other things, pathcast is also part of our system. So whatever method we are going to develop, initially we would see that how to solve this particular problem only, but after that
Okay,
we would see that whether my solving this thing is efficient or not. Okay,
okay, yes, okay, okay,
but
sir.
by answer
Understood.
to yeah.
Understood. Thank you, sir.
Yeah. So this particular graph actually shows that what is the terrain, how the things are there into the into the earth. That let's assume that this is the map, and the strategy that my agent is going to follow is this, that he is always going to take this shortest path if not traveled shortest path. So from Arad to Arad, when he goes outside, he can see the three places: 118, 140, 75. He go take the 75-kilometer route, reaches to Zarind. From there he takes a 71, because this is the only way he can take. He goes to Oradia. From there he take the 151-kilometer route. He reaches CBU. From there he takes the 80-kilometer route. He reaches to Valkia. From here he take this particular route and 97-kilometer he goes to Pitesti. From there he take 138 and 101. He takes the another route of 101 and reaches to Bucharest. This is how he reaches there. If this is the strategy, this could be a strategy. There is no problem on that. And by chance we have seen that he is able to reach that particular place, and he would definitely reach, because otherwise if there is no path possible explored, then he can come back and do something. It's a DFS kind of thing. So so this was the one strategy, but as you were asking earlier also, that whether it is a good strategy, no, it is not a good strategy. So we are going to see the search into more detail in today's class, and then let us also see one thing, that here there was a graph. On this graph you were searching that how to reach from one place to another. If we can somehow translate all the problems to the graph, then the searching on a graph is a general question, general problem. Okay, the multiple solutions are there. Then whoever solution suits us better, I can use that solution on this particular graph. So again, there is a uh, there is a there is a notion that if you want to solve a problem A, you translate to the problem B and you solve this particular problem B. Let's assume that you are only capable and you only know to solve the problem B. So if you have a problem A, so better way to translate this problem to B, and then you can solve it. So graph, finding out the path on graph is a very old problem and very general problem. So that's why we want to translate all our problem to the graph problems, and on the graph problems we want to apply some kind of searching mechanisms so that we can find out the solution. And if we can do it, then definitely we can solve the problem. This is what we want to do. Okay, so let us see another problem that is called the one minute. Yeah. So let us see another problem and try to see that how we can formulate this to our setting. Okay, how can we formulate it to the graph thing? So here this problem we have seen earlier also, toy vacuum cleaner problem. What was this problem? That there were two rooms, room number A and room number B, and there was some dirt into that particular room. Okay, somewhere there was a dirt, and we had a robot. So robot cleaner was there, and this robot cleaner was sitting in some of the room. So this robot cleaner can take three actions. What is those three actions? He can go left, he can go right, and he can suck. These are the three operations that he can perform. Okay, we assume that if he is here and he take right action, then he goes to B room. He goes to the B room, and he take left, then he remains into the same room. Okay, because he stuck to the wall and he remains into the same room. So these are the two operations that we can see. Similarly, you can here also see that if he take the right, he remains into the same room. If he take left, he crosses the room, go to the next room. Whenever he applies the stuck operation, so if there is any kind of dirt, that dirt is get removed. Let's assume that it gets removed. Now, what is the how can we model this particular problem? What are the different conditions which are actually possible? So you can think that since there are two rooms, so I can say in this particular way. So let me help me that whether I'm right or not. There are two rooms, na? So both room could be clean, or another condition could be that in one room there is dirt. Another condition that the dirt is into the room A. Another condition could be that both the rooms have the dirt. These are the four conditions possible. And in all these scenario, my robot could be into the room one, into the room A. It may be possible. Okay, so this is the one setting that I have. Another thing could be that I copy this thing, and another thing could be that my robot is going to be into different room. My robot is inside this room. Okay, so these are the 8 conditions possible. Everybody okay? Everybody okay? Any questions on that? So
Sir, Chandramouli, excuse me,
yes.
sir. Sir, can you able to explain this formula, sir? 2 into 2 squares equal to 8. Hello?
Yes, yes.
This formula is there, no? 2 into 2 squares equal to 8. This formula can you able to explain what is 2 square, or the 2 is what exactly?
Okay. So this formula, I'm going to come to that particular thing. Okay. So let us see that. Let us see this particular part that I have said that there are two locations in which this particular item could be. Okay, this particular robot could be. There are two locations. Okay. How many locations are possible? So in first place, it may be possible that there is a dirt or not no dirt. So there are two such choices. Okay, in the second room, there could be dirt or not dirt. So two more conditions are possible over here. So total number of conditions which are possible is 2 square. So let's assume we have 5 rooms. Okay, we have 5 rooms. 1, 2, 3. Now we have 6 rooms. Let's assume that we have 6 rooms. So how many different possibilities are dirts are there? How many different possibility of dirt are there? Here could be dirt or not dirt. Two ways. Here also dirt or not dirt, dirt or not dirt, dirt or not dirt. So 2 to the power 6 possibilities are there. Okay. Do I make sense? So in each of these scenarios, the robot could be here or here or here or here or here or here. So six different positions are possible. So this is the number. This is the thing that is going to be into your state space. Okay, this is the maximum number of things which are possible in your state space. Make sense? If I ask you the
The 6 is
if
a
I
room
ask
number, right, sir?
if I have 6 rooms, so
Okay.
just focus on this thing. If we have 6 rooms, then robot in each of these configuration, I can put the robot in the first room, then into the second room, that's the third room, 6 rooms. Okay, so this many number of states would be there in my state space. Make sense?
Yes, sir. Understood.
Okay.
Thank you.
Okay, so all these states, how many? 1, 2, 3, 4, 5, 6, 7, 8. So I am going to put here 1, 2, 3, 4, 5, 6, 7, 8. Eight different states are there. So all these things are here. So you just try to see this thing that if you are into this particular state, if you are into this particular state and you go left, so what is going to happen? You take the left. So you are not cleaning actually, you are going left only. So you remain into the same position. So I say I put the link in this way. But if from here, if you go right, if you take right, you this robot goes into this room and therefore this configuration come. Again, you take right, nothing is going to change. From this thing, if you take left, you come into this particular configuration. Yes or not?
Yes, sir.
So we are today we are doing child game. From this, if you can apply suck, this room, this dirt is going to be cleaned. Okay, so this is the configuration we are in. Here, if you take right, you are going to be into this scenario, take left into this scenario, take right, no scenario change. So by this, you can create this. Am I right or not? Yes or no? You can create this thing. If you take from here, if you suck, then this room will be cleared. You suck, you reach here. So this is called the state space diagram. In this state diagram, these two are the goal states. So either you reach into this state or this state, both are fine. So goal states are two. It is not only the every time the goal state should be one. So this is a very important example that tells you that your goal states can be more than one. Okay, so two states are there which are actually like that, and two states which are actually final states. Initial state, what is the initial state? I don't know. It could be any. Right now in our setting, it could be any. So let's assume you are here, then how to reach to this particular thing. So initially, any state you can tell that it is an initial state. So what is the problem this particular robot is solving? So in whatever state you are, you reach to here. This is what the problem he have to solve. If I tell that you are into this state, how to reach over there? He knows that if he in this particular state, you have to take left and then suck. You would be reach here. If this is the problem statement, how can he reach there? Suck left and suck. By this he would be able to reach this particular state and done. Okay. All right. So in the last class, I think we are at the right place where I can tell you one more thing that I can add page here. So in the last class, we were talking about a very interesting problem. At the time, I gave you this as a homework that is called water jug problem. Please solve this for me. So what was the question? So there was a jug with the 7 liter, I think. Am I right? 7 liter, and there was a jug with the 3 liter. And your task was to somehow get. Your task was to somehow get. 1 minute. What is happening? Oh my God, ऐसा तो होता नहीं कभी. What is this? 1 minute.
Good morning, sir. Saurabh here. I have a question.
Please ask.
Sir, in the last slide, you were talking about goal state. Both the conditions together makes a goal state, or any one of them can be goal state, sir, in your example?
Okay, very good question. This question you must ask every time. Okay, whenever you have a confusion, please ask. Okay, so goal state are both. I mentioned this also. I think you missed that particular time. Every time you please ask this question. It's a very important question. Goal state need not to be one. I actually emphasize on that also, that both of them are into the goal state. So goal
Together
state
will
is
make
actually
it as a one
final
goal
state.
state, right? So
No, not together. So in the final, in the set that I can say final state 1, state 2, two states could be there. So I can in the same way I can write S1, S2, S3, S4, S5, S6, S7, S8. I can write like this. Na? I can say that S7 and S8 are into the final state. So together, how can you be into the both the states? You cannot be into the both the state. You would be only one state. Okay. At one point of time, you would be only one state. So final state contains both. So that's why in whatever state you are, if even if you are into this S7 or S8, you are okay. That does it make sense?
Got it, sir. Thank you, sir.
Got it? Good. Okay, so so this was the problem. Let me copy it. Let me paste it. Okay, let me keep it here. So what this was the problem in the last class, we have actually discussed that I have a vessel of 7 liter, another vessel of 3 liter. And now I want, and what is the choices I have? What I can do? If there is some water over here, I can pour it here. If there is water over here, I can pour it here. I have a tap. There is some outside tap is also available. From there, if I go there, I have to fill it. I fill it full because there is no markers on this. OK, there is no markers on them. So if I fill it half, I'm not sure that how much it contains. OK, so every time if I go to the tap, I have to fill it full. So this is the one scenario where nothing is there. And my answer state that I'm going to ask you is this, that can you 1 minute, can you copy paste key? Can you give me 1 liter over here? Can you 1 liter of in 3 or 1 liter of this? This is goal state, or another could be another goal state could be 1 minute. So drawing becomes very difficult. Okay, so let me draw once again that this is 7 and this is 3, and I say that this is 1 liter is here. Both are actually the fine thing. Okay, both I'm telling that they are okay. So these are the final states. So what are the total states? In the last class, I have given this problem to you. So you can say, sir, this is the state number 1. Let me say that state number 1. From this state where you can go, let me try to draw it. Okay, because I am feeling very uncomfortable in doing this. So let me draw one by one. I would not do fully, but I need your support to draw it. So what is the next state that I am going, and I'm going to fill this one full. Okay, fill this one, and the second one remains the same. There's 2 tasks I cannot do at the same time. Okay, this is the one thing. Another that I can go to another state, that is where I say that this I'm going to fill the 3 one. Okay, this another one that I say that I'm going to fill this one. Okay, from here I can go here. No, I cannot go here. So after doing this, what I can do, that I can go and fill the second one also. Okay, so this was the S3, then S4. S4 says that this and this. I say that this was already filled, but this time I'm going to fill this one, another state, S4. So I can say that from this state I can reach to this particular one. Okay, I can reach from here to here, and then from here I can reach. From here I can put all these water into the previous one. I can say that this becomes empty, and 3 liters goes here. The 7 one 3 liter goes. So what I did, I have emptied the smaller one into the bigger one. Okay, and from here I can reach where? From here I can reach where? I can reach here, that I can say that if 3 liter I fill it here, so then 4 liter would be here. Okay, give the name to all these states. That is not a big thing. Okay, 4, S5, S6. So I'm not going to solve this particular problem completely, but if you do something, I don't know, there would be some states where there is only 1 liter in one and another is vacant. Okay, so one more thing I wanted to tell, that you can fill it from some source, and you can spill all the, you can empty your vessel in some sink also. So there is a sink where you can And let's assume that there is a tub and where you can put all the things once again, and from the tub you can fill it full. So this is what the scenario is. How to reach to this particular place is not known to me. I don't know that from here to here, what are the actions I need to do. So now you understand that how can we draw the graph? Is it clear or not? Yes. This water jug problem,
In
how
previous
can
example, sorry, sir.
yes.
In previous example, we saw that the two states attach point,
Uh-huh.
starting from S1, S2 to S7, reaching at S7 and S8. So in the
Mm-hmm.
current example,
Mm-hmm.
are we fulfilling this criteria to have two states at each stage? Sorry if I'm
Uh,
missing anything, sir.
no, I think here 8 states were there. Okay.
Right.
And here how many states are there? We are not sure about this. So let me try to find out that how many states could be there. Okay. To
G,
please
sir.
help me if I'm wrong. So
Sure, sir.
there are two vessels. Okay. There are two vessels. In one vessel, what is the possibility? 0, 1, 2, 3, 4, 5, 6, and 7. In second vessel, what is the possibility? 0, 1, 2, 3. These are the possibilities. So total number
Right.
of ways which are possible is 8 multiplied by 4. 32 states would
Correct.
be there. Am I right?
Yes,
How they
sir.
are connected, you have to find out this. So these many number of states are going to be. Now you have to figure out that how to find out this. Some of them may not be possible. Okay, with this is the total absolute number of thing, but some of them may not be reachable. It may be possible that there are some states, because I'm just telling that all these states I am enumerating. So from starting here, it may be possible that there is no way you can reach to another thing. Okay. Right now,
Correct.
I'm not talking that how to find out the solution. You know that how to find out the solution. Okay, that's very easy. That you know that you say seven thing is seven. Take the 7 letter, pour it here, then
We can take the combination of, sir, the last of first and the last of second.
just do
So we
this. Nah,
can make the
just fill the 7 1, and
yes,
then you
zero.
fill the 3 1 and empty it. Again, you fill it. The remaining
Right.
is going to be 1 liter. That's it.
Correct.
That's gone. Okay, so I'm not going to ask the solution right now. If you represent the things over here, you can apply some standard mechanisms to find out the solution. That's it. That's the point is. So let us see. We have seen two problems. Let me give you another problem. That is called the 8 puzzle problem. Everybody, have you seen this earlier? So it is a kind of 3 by 3 grid where there is one hole. Okay. So what you can do that you can slide is here. You can slide it 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 here. So let's assume that when you slide it here, what it becomes? 7 2 4 5 6 8 3 1. Am I right? It becomes something like that. Have you seen this toy? After that, you can slide
Yes, sir.
7
Yeah.
down.
Yes, yes,
Then
sir. We have.
it becomes 2 4 7 5 6 8 3 1, something like that. So this is from one state to another state. I'm going, one state. And goal state is this. At the end, you have to reach to this particular place where everything is 0, 1, 2, 3, 4. Everything is arranged like that. This is the goal state. Okay. So again, I have the same question that how many states are there? How you formulate the problem? Right now, we are actually trying to understand that how we can formulate the problem. If you can formulate the problem, as I told you that any problem that you have, you can formulate this into my known ways, and the known ways is definitely into the graph way. Then you can apply the standard method to find out the solutions over here. Okay. So how to formulate this particular problem? You understood this problem? How can you formulate this particular problem? So once again, let me try to give you some kind of understanding that this problem is very simple. Which means the boys play this thing. So you can simplify it more and tell that the number are 0, 1, 2, 3, 4, 5, 6, 7, 8. So if I write something, for example, 3, 2, 1, 0, 7, 5. Oh, I'm doing wrong. One, two, what number I missed? 1, 2, 3, 4, 5, 6. I think 6. So 1, 2, 3, 4, 5, 6, 7, 8. All the numbers are written. If I let's assume the numbers are coming from this, and whenever I write into this particular way, it can be translated to a grid, and where I can say that the first number is going to be here. I say that this first number is going to be here, second number is going to be here, third number is going to be here, fourth number is going, this is the blank. 0 means 0 represent blank, then this represents 7, then here it is 5, then here is, so I missed something. 1, 2, 3, 4, 5, 6, 7, 8. I must have 9. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so 4, 6, and 8. So this is what the position is. This is all the position. Okay, so any string, what I wanted to tell, any strings, any permutation of 0, 1, 2, 3, 4, 5, 6, 7, 8 can be represented to one of the problem statement. 8 puzzle instance can be represented as one of the instance. So you, for example, here 3, 2, 1, 0, 7, 5, 4, 6, 8 is this. Okay, everybody okay? Everybody okay with this? Okay, this statement is okay. So how many states are possible? If I ask you that how many states are possible, so you can say, tell, sir, how many permutation are possible? Okay, if I come up with any kind of permutation, I can create this instance. So how many permutation are possible? The question actually changes that how many permutations are possible. So let us see that how many permutation are possible. To make a permutation, how you go ahead, that you try to see that at what place, how many. I think 9 spaces I have to make, so it becomes 8, 9. So you want to ask that, sir, at first place how many numbers I can write. So 0 to 8 there are 9 numbers, so 9 numbers you can write. At the second place, since one number you have placed, so 8, you can pick any number out of the 8 available. Then here 7, then 6, then 5, then 4, then 3, 2, then 1. So factorial 9 number of states are possible. Everybody okay? Okay, this factorial 9 things are possible. So see how difficult this particular problem is. So everything is going to represent a string, and you know that from here you cannot go here because you can only shift this particular 0 to this place or this place or this place or this place only. So for example, when he is in the middle, there are 4 choices, but when he is here, only 2 choices are there. So some places, and when he is at this particular place, then 3 choices. Somewhere it has a 3 choices, somewhere it has a 2 choices, somewhere it has a 4 choices. So every node is going to be connected at most 4 different things. Okay, so this way you can draw this particular way. Okay, so this particular part is clear. State is factorial 9. Yes or no, everybody? Good.
Sir, here factorial only 8 numbers are there, no sir? That's dice.
Factorial 8.
But here, how come it will be 9
No,
numbers?
there are 9 numbers because 0 is also there.
Okay, 0 also.
And 0 represent what? Blank.
Empty spot.
You must have to represent that also. Otherwise, how can you? Otherwise, you'd lost this particular thing. Now, every representation. Now, look, numbers are not like that. You have also seen that there in this there could be an image of something, Taj Mahal image, and now you have to make the image of Taj Mahal by sliding this. So images are just placeholders. These numbers are only placeholders.
Okay,
No?
sir. I understand.
Yeah, I have a question. What is the initial state? I don't know. The problem instant. The problem that would be the problem instance. That would be the problem instance. For example, if somebody give me this thing to solve, then this is the initial state. Okay, if you give me this one to solve, then this is the initial state. So any of the state could be the initial state. Okay, what are the actions available? Give me. They are left, they are right, they are up and down. 4 actions are possible. Only these
But
4 actions
that's
are
depend
possible.
on initial state, right, sir?
That depends upon initial state. I don't understand what you want to say. Please
No, so
elaborate.
if blank is on top, we have only option of
Mhm.
left and right. Blank is
No, no,
in
no, no,
middle,
no, no,
then we
no, no,
have
no,
left,
no,
right.
no, 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 no. Here also,
I think all possible actions
left.
is the question, correct?
If you take the right, na here, you stay into the same position. The same
Okay,
concept here.
okay, got it, got
If you
it.
take left, you are into the same position. So these 4 actions are there.
Okay,
Okay. What is a transition model? Transition model is again you draw this particular complete thing and you tell that from here I go here, here I go here, which are things are connected to whom. This is the transition model. Okay. What is the goal test? Goal test, how you test that you whether you are into goal test or not. Again,
numbers
you
should be in
match with this.
sequence, right?
Yeah, you find out the representation. Let me say that. Let me forget about this thing. Okay, just represent this thing that from this whether this is the state or not. So goal state I can define. You can just one by one compare your representation with this statement. Goal test is possible. So you have to define all these things that when you want to solve this problem. What is the path cast? For example, when you are into this particular state, you reach to this particular state, you come up with a solution. What is the path cast? Number of steps required, huh? Number of moves that you are going to take. Make sense?
Sir, one
Yes.
question, sir.
Yeah, please.
Sir, related to actions, you said that left, right, up and down is the actions, right? Sir,
Yes.
were you talking about the possible actions or is it based on some position? Because you said that at some point of time there will be only 3 possible possibilities. There will be 4 possibilities based on the position of the empty spot, correct?
Okay, so we can let me correct myself. I meant to
Sorry, sir,
say
I'm just
that
trying to understand the third
no,
bullet point.
no, it's fine, correctly fine. Okay, we are on the same level. Please don't think that I'm any level ever than you. So I can also do the mistake. So so what I meant was that um, these are the semantically different thing. Okay, so here also, as I mentioned, that here also you can take the left move. Here also you can take the left move, but left move would leave you into same state. Here also you can take the up, but up move would leave you into the same state. I'm not telling that right now. I'm modifying my statement and telling that you can take all the actions in all the states, but some states after taking that thing, your state is not changing. This is only the thing. Because
Okay, got it,
by
sir. These
this
are the
we are more
got it.
general. And the same thing as I mentioned, that same thing was actually shown over here. That if you go into the if here you take the right, you remain into the same one. Okay. So by this we can
Got it, sir.
easily
Thank you.
formulate the problem. After formulating the problem, how can solve this thing is a different thing. Okay. So before going to the next slide, let me tell you one more thing that is very interesting to tell. And sorry. Okay. And this is that this number is wrong. And the reason is that semantically you can find out all things, but actually what happens now, if you start, let's assume that you start by this particular state and you do something, what you can do, you can take it up. Okay, let's assume that you take it up. So 1 minute, what I wanted to tell, this that this particular state has a signature that is 0, 1, 2, 3, 4, 5, 6, 7, 8. But when you take this 3 up, there are 2 things possible. Na? Three semantically correct things are possible. Either you take 3 up or 1 into this particular direction. So I can say into this particular way that the blank is being shifted to left or right, or blank is shifted up or down. These are the 2 things possible. Okay. When you shift it left or right, so what is going to happen? So let me forget about this. Let me think that let me consider this one first. So when you shift here, it becomes 1 0 1 2 3 1 2 4 नहीं नहीं गलत किया मैंने. Why I written 1? So this is going to be 1 0 2 3 4 5 6 7 8. Okay. So this is going to happen. I am going to define something called inversions. Inversions means how many places the order is not correct. And you know the order. Order is means 3 should come after before 4. Okay, this is called the correct thing. But if I say 4 3, it is an inversion. 4 3 is an inversion. How many inversions are there? So there is here in this particular case no inversion is there. Everything is correct into the order. And if I change in this way, 1 minute. If I change into this particular way, then inversion are not going to be affected. Okay, if I further change it, further shift it, it becomes 1. It becomes 1 2 0 3 4 5 6 7 8. If space comes, if space is from here to shifted here, I got this representation. In the second representation also, there is no inversion. Am I right? But when I go
Sir,
from
can
up
the
to
0
down,
and 2 not be considered as inversion?
no, because 0 is a whole now. Consider the number.
Okay, got it.
Okay, 0 is a whole. So now, but when you take it up or down, what may be possible? If you take up, then you get this sequence 3 1 2 0 4 5 6 7 8. Am I right? When you take 3 up, when you take 3 up, yeah, you get this thing. How many inversions are there? How many inversions are there? So everything remains the same. Only the thing changes into this particular region only. Only thing changes into this particular region only. And it comes before these two items only. So every time, even if it was here, it comes here. So it comes before the two items. When the item was here and you shifted here, to this particular item comes before these items. So every time, whenever you are going to shift this thing, and even from top to down, so the sequence is going to affect only two items from where the two inversions are going to change. So either you are going to, it may be possible that there is a zero zero change in inversions or two change in inversions. This is the only thing is possible. Either there is no change or there is two change in inversions. This is only going to happen. What I wanted to tell. Let's assume. So here, how many inversions are there? Can you find out that? How many inversions are there? 3 1 is an inversion and 3 2 is an inversion. Am I right or not? 3 1 and 3 2 are inversions. These are the two inversions that we have. Any other inversion is there? Do you understand this? Everybody. When you shift, once again, when you shift this 3 up, 3 comes before these two items. So it can affect these two items. So two inversions can be possible. Every time two inversions can be possible. So either it increases two inversion, or again, for example, into from this particular state, you can again go to this particular state. If you go this particular state, what would happen? Two inversions are reduced. Okay, so it can increase -2, +2, or 0. So every step is going to increase your inversion by 2, or does it may also be possible that there is no change. This is the only thing possible, everything. Okay. Are you able to understand this? Yes or no, everybody? I would not go into much detail. So this was the technical detail that I wanted to tell you. So now please tell me that my question is that if I come up with any this thing, okay. So if this is the initial thing. From this thing, you go to this particular state where the number of inversion is 2. Then you change something, your number of inversion is 4. Then you change something, number of inversion is 2. You change something, number of inversion is 6. Then 8. Then 10. Then something. You are keep changing. And now you are into this particular state where number of inversion is 44. and I give this thing as your problem. I give you that this is the problem that is given to you. Your task would be to change it so that the number of inversion becomes 0. When the number of inversion is 0, you are definitely into this particular state. Am I right or not? Am I right or not? Every time your number of, you have to change this number of inversions so that it becomes 0. When it becomes 0, you are into this particular state and you have actually solved your problem. That's it. But here comes a catch. Everybody, please focus. Here comes a catch. Can I create a string that have odd number of inversions? Yes, I can create it 2, 1. Here, if I write 2, 1 instead of this, I can write 0, 2, 1, 3, 4, 5, 6, 7, 8. How many inversions are there? There are 1 inversions. But you know that by doing right kind of thing only, by doing right kind of things, only odd inversions can be even number of inversions can only be obtained. So this is an invalid. This is an invalid representation. This representation is never going to come in your front. If you start by this, keep inverting something, you cannot reach to this particular state. So they are unreachable states. So there are few unreachable state. And how many states are there? Half of them, because even if there is even inversions or odd inversions. If even number of inversions are there, then actually this is the valid position. If odd number of inversions are there, then it is not a valid position. So what does mean? It means that number of state which actually we were counting as factorial 9 is not factorial 9, is actually factorial 9 divided by 2, because half of them I cannot reach. Once again, my question is, in 8 puzzle, how many valid states are there? They are factorial 9 divided by 2. Yes or no? Yes or no? Everybody, factorial 9 divided by 2. It is not factorial 9. So few minutes back we are talking about, we have shown you that it is factorial 9, but it is not factorial 9 because there are, you can create some of the states which are not reachable. Make sense? Okay, thank you. Any questions? Hope you understand this part. And after everything is fine. Okay, you define this thing and you must understand that how many states are there. Everything is, if you define, then we can apply the searching mechanism. All right, so
Sir,
this is another problem.
So can you repeat that
Yes.
even and odd inversion thing?
Yeah,
Sorry,
everything is recorded. Please focus on this. Otherwise, what would happen? The people who would see the recording, they would curse me. Okay, once again, give me. Yeah, let me tell you once again. Okay, the point is this. The point is, who are asking the question? I'm sorry, I'm not pointing you. I just wanted to discuss with you.
Yeah.
Aditya. Aditya?
Yeah. Yes,
Aditya. Tell me this thing. You understood this particular part, that when I change this into, when I change my blank space into left and right, there is no inversion. Yes or no? No inversion. You understand this particular part? What is inversion? That at how many places the order is changed. Okay. For example, into this, 2 inversion are there. 3, 1 and 3, 2. 3, 1 and 3, 2. 2 inversions are there. Okay. So how many inversions are there? I wanted to find out the number of inversion. You can, if you slide this blank one into left or right, there is no inversion is going to change. Number of inversions are not going to change. But if you take up or down, inversion can be increased by 2 or they can reduce by 2. Okay. So change is what is the change is possible, that whether the inversion is going to be increased by 2 or decreased by 2. So for example, when I take it up, I reach into this state, number of inversion was 0, it actually increased by 2. But when I take, when in from this state to this state, when I go into this state, I'm going to reduce my number of inversion and it becomes 0. So Adit, is it clear?
Sir, 0 is not counted for inversion.
Say, 0 is not counted. I told you that I'm just counting the numbers. Okay. Okay. So now if you understand this particular part, Aditya, so can you tell me that since here the number of inversion is 0, whatever operation I'm going to do, I'm going to add 2 or subtract 2. So number of inversion, whatever I'm going to take, is going to be positive number only.
Yes, correct.
Even number only. Even number only.
Even number, yeah.
Even number
Yes,
only.
correct.
But I can deliberately create one inversion. I just give an example 0, 2, 1, 3, 4, 5, 6, 7, 8. I can deliberately create. If I create this thing, you know that there is a direct mapping, and by this I can get a problem statement. Okay, but that problem statement, whether this problem statement is valid, answer is no, because it has a number of inversion that is odd. It is not possible because from this state you cannot reach to that particular state. That's it. I wanted to make it point. What point
Okay,
I
sir.
make?
I got.
Okay,
Yeah, I
you
got
cannot make, you
clear.
cannot reach to this state because every time even changes you are going to do. How can you reach to odd? So by this, half of them get invalidated. You cannot reach to those states. So therefore, total number of state is actually factorial 9 by 2.
Makes
Done?
sense, sir. Yeah. Yeah.
Thank you. Next problem, 8 queuing problem. It's very simple problem. Okay, 8 queuing problem is very simple problem. So I have a chessboard. I have a chessboard where I have 8 queens, and you know that into the game of chess, queen is the most powerful thing. So when queen is here, so it can attack anything which is in this particular line. It attack anything in this line, attack anything in this line, attack anything in this line. So am I right? Attack anything in this line. So if I have 8 queens on the chessboard, so if I put one queen, if I put one queen here, so can I put another queen here, here? No, they cannot sit. I cannot put another queens here also. I cannot put here also, but I can put here. Second queen I can put here. So if in this way 2 queens are placed, where can I put the third one? Can I put third one here? No, here. I think here I can not put, but here I can put. So here I can also not put. So you understand the problem that third one I have to put. So maybe I'm going to put it here. Okay, am I right? Third one I can put it here. No. You were telling sir, क्या कर रहे हो?
It is not visible.
Not visible. Okay. So let me. I don't want to draw it, but let me do it for you. 1, 1, 1, 1, 1. Okay, so I'm wrong. Let me give it in this way that I say that first one I'm going to put it here. Okay, second one I can put it. I cannot put where. Let me draw a line. I cannot put it here. I cannot put it here. I cannot put it here. These things are I cannot put. So whatever I put, I placed it here. Second one is here. Okay, everybody. Yes or no? I can put it here. Second queen I can put it here. Okay. So if I put it here, then I cannot. Third one I cannot put it here. Third one I cannot put it here also. So let me put third one here. I'm not going to solve it. Okay, it's going to be very difficult for me. So I think you may be better than me. So find out that what is the best way that you can put 8 queens on the same board and none of them are attacking to each other. This is the problem. Okay. You understand the problem? I'm not going to solve it. Do you understand the problem? Yes or no?
Yes, sir.
Okay. So what are the states? Tell me. If I ask you that define this problem, what are the states?
The configuration of queens.
Configuration of queens. So how many states are there? My question is actually how many I should ask in this particular way. So first queen, Q1, Q2, 3, 4, 5, 6, 7, 8 queens. First queen you can put in any place, 64 places are there. Second queen you can put 63 places. Third one you can place 62 places. Fourth one you can place 60 places. Fifth one you can 59 places. Sixth one you can place 58 places. Seven one you can place 57 places. Eight one 56 places. Total number of states is the multiplication of all these numbers. How many of you agree? Number of states is this, but they are not solutions. So definitely, you know that goal state. What is the goal state? I don't know, but none of them are attaching to each other. How many goal states are possible? There could be many, but at least I can tell you 4. Yeah, tell me. Yes, somebody was speaking. Yeah. How many goal states are possible? At least 4, because you know that if I say that if I say this AB, then I can create another board position where I can put AB here. I can just rotate it. I can just rotate it AB here. I can just rotate it AB here. So all those things are valid board positions. So at least 4 positions would be there. 4 goal positions would be there. There may be more. Just find out that how many of them. So there are many. So how can you solve it? I'm not going to tell you, but one method could be branch and bound. You know that you are going to put the first one here, the second one try to here, so that if there is attack everywhere there is attack. So you first find out this place where there is no attack. You put the second one, then start putting the third one here. I think here you can put. Then the fourth one you try putting here. Now after that you cannot put anyone. Go back. You take it forward like this. Some branch and bound, different kind of mechanism you can apply. All right, what is the initial state? Blank board position. Initial is the blank board position where nothing has been left, is there. Okay. One by one, you are going to introduce the queens and you are going to see that where if they are not attacking, you can put the another one. What are the action? Action, you can tell that when the second one I'm going to put, I can put it here. I'm forwarding it from one place to another, one place to another. You're going to find out the search the position, the forwarding the position. What is the transaction model? Oh my God, these many number of states you have to make, and then you have to tell that from this board position to this to this. It becomes very difficult. Okay, but these are the transaction model. What is the goal test? How you can test that you have reached to the final thing? That's very easy. See, if none of them are attacking to each other, problem is clear to everybody. Please ask the question if you have any doubt. Okay, this is how you formulate this particular problem. These things you have to tell, and by this you formulate the problem. Okay, how to find out the solution? We would talk about later that when you formulate this problem, you created the transition model, then on this transition model, you would run a search. Okay, we would come back to the search in more details. Any questions? Happy? Yes or no? Am I boring you?
No, just one
So
question.
let me. Go
Sorry.
ahead. Go ahead.
I could see some examples in the bottom. H equal to 0. Is that relevant to this? Some board positions.
Yes. So how many attacks are there? So this is an example where actually I forget to mention. This is the board where 4x4. Here 8x8 thing is there. Na? This is the 4 queens problem where 4 queens you have. Okay, so how many attacks? You can define some number h that can tell that how many attacks is there. So here how many attacks are there? 0. So this is the right answer. Okay, so here how many attacks are there? 2 attacks are there. If you put the things into this particular way, 2 attacks are there. Here 5 attacks are there if you put into this particular way. So somehow you define that how many attacks are there and they are going to reflect you with respect to the goal one and you want to make it 0. Make sense?
I got it. Thanks.
Good. So let me give you another very interesting example. And this is called something called the Knuth conjecture. What is Knuth conjecture? It tells that 4 is a very important number. Which number? 4 is very important number. Interesting number. I give you 3 operations. 3 operations. Okay. What are these operations? You can apply factorial. You can apply factorial. You can apply square root and you can apply floor operation. Floor operation means 3.92 becomes 3. 8.001 becomes 8. 6.5 6.5232 something becomes 6. Floor. Am I right or wrong? Everybody knows floors. Okay. So this is what the floor operation is. So I am going to give you three operations. What are these three operations? Factorial. You can take the factorial, or I can write it like this. You can take the square root, you can take the square root, or you can take the floor operation. These three operations you can apply. So everybody, please focus on this. There is a very interesting number 4. You can apply what? Square root. If you apply, I told you that you can apply three things. So if you apply square root, you get what? 2. If you can apply lower, okay, so floor you get the same number. Okay, with the 4 you get the same number. Okay, next is the factorial. Factorial of 4 is how much? Can anybody tell? 4, 3 into 2 into 1. 24. You get this number. Everybody. Is it okay? No. Is there any problem?
Yes, sir.
This is what the factorial is. So you keep doing. Who is stopping you? You apply once again the factor here also on the 2 also you apply factorial. 2 factorial becomes 2 only. Huh? Am I right? The square root of 2 is what? Square root 1.44. So if you apply the square root on 2, you get 1. No. Oh my God. You apply square root, then you get 1 point something something number, and then 1.44 you get the number. Then you apply floor on this, and by this you get 1. Am I right? Okay. By this you got 1. And similarly on 24 you can apply all these operations. Do I want to go more? No. Okay. So here you can see that you got 1. Somewhere you got 2. Somewhere I don't know if you create something somewhere you. Oh my God, what I did. Okay. Somewhere you can get 3 also. How many of you agree? Somewhere I can get 3 also by doing something. Yes or no? Somewhere you can go to 4 also. Everybody, please participate. I'm asking very important question. Everybody. You are not, everybody not happy. Tell me. People are confused. Okay, somewhere I can get 88. Okay, somewhere you can get 105. Somewhere you can get. So can you get all the numbers? Can you get all the numbers? Whatever number I say, 3, 4, 1, 2, 5. Can you give me this number? What can you get all the numbers? Yes or no?
Probably.
Yes. Yes. Say again.
Probably.
Probably. Okay. Nut says yes.
Sir, primes can't be here, right?
Primes cannot be here. 2 is a prime number or not? So let's debate on this. But 2 is here. Okay. Okay. So what I wanted to tell you that Nut says that in
the square root of 24.
Can you please prove? Can you please prove? $1 million you would be given, and you would get a very prestigious prize in the computer science domain. Just prove that 3 cannot be obtained. So that's why somebody is clapping. Just try to prove that you cannot get any number. Just prove I cannot get 3. Just this. Okay. Any desired number, any desired positive number you can find out by this. This is a node conjecture. There is no proof. You can prove, you can get a huge sum for that. Okay, so how to get 5? How to get 5? So it is written on the board. Okay, how to get 5? This is how you get 5. Factorial 4, factorial, apply factorial 4, then apply factorial on that. Apply multiple number of 1, 2, 3, 4, 5 times under root. Take the floor of this, you get 5. So this is what this North conjecture is. A very strange kind of phenomena. Okay, but what are the states? Now define with me. What are the states? They are numbers 1, 2, 3, 4, 5, 6. All the things are there. Just imagine that there is all the numbers are written on the sky. You are lying down in a fine night and you are seeing the sky in front of you and all the numbers are written over there. So they all are the states are the numbers. What is the initial state? 4, because you start by 4. It is telling that I'm going to use 4 to generate any number. What are the action? 3 kind of actions you can take: under root, factorial, and flow operation. What is the transaction model? We have to come up with that because we have to make it. Okay, you have to make it. You have to apply different operation, different kind of operation. So as I told you that different kind of, you keep expanding this particular graph and you are going to take infinite time to find out. You need infinite time to create all these connections, but after that you would be able to make it. Okay, transition model, you will be able to make it. What is the goal test? Goal, definitely person is going to define that I want to find out this number, and for those numbers what are the operation need to be given, this you have to tell. Different kind of problems we have seen today. Yes, there is some raises hand, please let me know. Rudrani, do you have any question?
Yes, I've
Rudra.
been meaning to. Yeah, I've been meaning to ask this question for the past few like models we were seeing. Uh, the goal is our responsibility, right? That we need to decide like what do we want out of the system. That is correct. But the transition model or the state space, whatever is created, or like who creates that, or whose responsibility is that? Like, do we need to specify it, or the system will specify it in itself and then process upon the goal?
It depends on the problem. Na? If look, when you define the problem, you actually give the blueprint of making all these things. So that's why here is a something called formulate the problem. In this thing, there is something called formulate the problem. I think now you can understand better. What do I mean by formulate problem? Okay, when you define the problem, by this problem definition, you actually give the blueprint that how to create all these things. They can be infinite states. Here only 8 states were there, but here you can see that how many, here you have seen how many states, 32 states were there. Here how many states were there? Factorial 9 by 2. And here again, there was a finite number of states. And here infinite number of states are there. Infinite number of states are there. Different kind of problems, different flavor of problems.
Right, so like if we start and start to define the states and then start to solve the problem, then this is like this problem might not be solved. Then in this particular thing, we need to include the goal test along with the creation of the transition model or along with the problem formulation. I mean,
Yes, but
this is where
now
it
you
is.
are thinking, but now you are thinking in terms of finding out the solution. Okay, you discuss more about later. Okay, how to find out the solution. Right now, just try to understand that what is the problem. Okay, just try to understand this particular part. Finding how to find out the solution becomes very difficult, and this concern that you are actually raising can be answered using, you know, that there is something called lambda function into the Python. They tell that I have not explored until it is required. Understand? So sometime if you want to solve this kind of problem, infinite space is nowhere available. So if it is required that, for example, whenever you are applying any kind of function, anything get generated, then at that time you are only going to create that particular state. Some few states which are not reachable, I'm not going to create them anyway. Make sense? So yes, definitely sometime in the scenarios when you are actually having the lot many number of states, you are not going to generate them. You want to create some mechanism by which you are going to only generate the relevant parts of that thing. That is required, and that's why the different kind of searching mechanisms are going to be explored. So sometime just think that in some setting where the infinite things are possible, if you apply some kind of methods, you would not be able to solve this. But some other searching mechanism may give you the solution. We are going to see that. Did I answer your question?
I have a doubt.
Just yeah, please ask.
Yeah.
Please ask.
So for example, like most of the chess games that we had like in the past and currently we have in our mobile phones, So the AI algorithm actually, have a levels, so that how deep it is going to look into. So that is so basically, like whatever the set of actions that it can take at the current state. So from that state, taking on any action, it can go to some other set of states. So those other set of states are transition model.
No,
That is the
states
question.
are states. No, states are states. Okay. So what happens? Look here in this example. I think. Oh my God. In this example itself, let me tell you this thing that what we can do. That look, how many states are there? 1, 2, 3, 4, 5, 6, 7, 8. Dot 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 dot. Different states are there. Okay. But if I say that you can only apply 4 operations, this is what you are telling. Okay, then
These are the
definitely
actions.
Different actions I can apply, 4 actions you can apply. Then definitely this particular infinite set reduces to a smaller set. Okay, and you are only moving into this. So if you apply this, you are going here, you're going here, something like that. Okay, this is what the scenario is. This is what actually you want to talk. You are actually talking over. And please, everybody, please understand that what is the question that he has asked. After some time, you'd be seeing some methods that actually want to work on this particular thing, because if you don't restrict this thing that I'm going to use only this 5 depth or 10 depth, then infinite number of things are going to be required, and then you would be not be able to solve the problem. Even for the first, if I give you the board position, you will not be able to tell that first move you cannot make. If we restrict our thing, then only we would be able to make any kind of progress. So later it would come. Okay.
So sir,
So
what
whether
is
I have
transition model here? Yeah,
transition model,
my
okay, transition model is this. Transition model is this. From this you go here, if you take this action you go here, if you take this action you go here. This particular graph is the transition model, that how the things are linked. This is the transition model.
Okay.
This is a transition
Basically, to reach that state in the
model. States,
future.
different states and their reachability, their
Okay.
connection. Yeah.
Okay. Yeah.
Okay. All right. Very good. Excellent. So multiple problems are there, such as route finding. For example, route finding, you know that if you are here, you want to go from here. What is the route? Towering problem, you know that most of the time people say that if there is a graph, I want to visit all the streets, or want to visit all the cities, and all the cities with the smallest numbers of moves. So all these conditions can be applied on that, and they actually give a different flavor to the particular problem, such as Euler walk or the um, traveling salesman problem, or different kind of things. So there is another problem that is called the VLSI layout, that says that if you have a microprocessor, if you are designing, so some component is here, so you want to keep the 5 registers somewhere. So if, because they are going to be physically present somewhere, if you want to read things, so the line is going to be larger. So where you should put so that the minimum energy consumption is required. So that is also a very important thing. How can we find out that? Um, what is the robot navigation, if there is some scenario is defined and robot need to go from one place to another, so different kind of challenges could be there, how to come up with them and find out the right path. Automatic assembly sequencing, again, once you know that the different parts are there, if you keep arranging in any order, for after that you would be stuck that you cannot fit this particular part. So a special kind of arrangement should be there, then only you would be able to assemble all the parts. So all these things are known to you. So these things are there. Okay. So if so for all these problems, you need to define all these things, that what is the initial state, what is the final state, what is transition diagram, and then by this you can find out the better layout and some methods. Okay. So here, very important thing is this, that that if you divide the, and if you devise the problem into this particular way, then you can tell that I am into some state. And from this state, there are few options that I can take. Okay, from everything I can take few actions, and options means actions that you can take. If you take this action, then you are going to into this particular direction, and again a new tree comes to you. And if you come into this particular direction, again a new tree comes to you. So once again, I wanted to tell that let's assume that these are the states, for example, these are the states, and let's assume that there is some connection between them. And let's assume that there is some connection, and you say that I start by this. So you put it here. So there are four ways to go. So you put four ways. If you go into this particular way, again, there are four ways. So again, you could put four ways. From here also, you can put three ways. So again, here also, you can put three ways. From this, you come here. Again, there are four ways. And from here, there is one path that goes here. Again, you are onto the same place. Again, the same tree repeats over here. So every tree you can think that it is going to be infinite representation of the problem. But in between, if you don't go into the right way, you would be circulating into this particular thing only. You need to apply some mechanism so that you don't repeat this particular thing. Okay, so in essence, graph can be converted to tree. Yes or no? A very important point I'm telling. Okay, graph can be converted to the tree. Yes or no? Everybody understand this part? Graph can be converted to the tree. So this is what I told you. And here there would be repetition. I'm not telling that there will not be repetition. There will be repetitions. So if you are, your studies should take care that you should not repeat the thing. So my problem was to reach to the Bucharest. Three paths were there. If I select this particular one, I am going to so how I am going to proceed? I am going to create something that is called frontier, and it is a technical name of just maintaining a priority queue. Okay, which item I'm going to take next. So I have a frontier. Initially into the frontier, I would put Arad that I want to. I have only Arad to evaluate, but I would take the Arad out and I would put the Cebu and Timisoara and Zerind into my thing because Cebu, Timisoara, Zerind are there. I put them into the thing. Then I consider this thing. My frontier says that consider S. Then I would from the Cebu, I see that four places are there. I put 1, 2, 3, 4 places into here, and then I consider them. Should I put it before? Should I put it here? All these things depends upon the strategy that I'm going to follow. So there is something called frontier. Everybody try to understand what is frontier. It is a technical name in our domain, in AI domain, that says into the priority queue, which is the item that is going to be given to me right now. So frontier actually says that initially you actually are here. Then this is the frontier. Then when you explore this thing, you selected that I'm going to into this direction, and you are telling this thing. Then frontier is this. Then this is the frontier. Then you find out that okay, no, this is not good. For example, somewhere you come here and you explore this thing, then your frontier is here. So you keep expanding your frontier, and at the end you would be hitting some point that is actually your solution, and you got the solution like that. Okay, so the search, what is the search? That you are going to give the problem, and after that problem, it is going to do a graph search, and you are going to give you the solution. And not go into the detail, that is not required at this particular moment. What you have to understand that there is something called frontier, and you advance your frontier, and this is how the frontier get advanced, explode things. And after that, you are going to see that these things I'm going to explore into frontier. Whatever points are there, I'm going to use them to advance my search. Make sense? So one very interesting algorithm that all of you know, that is called the best first BFS. Okay, so uninformed search strategies. This line may be new for you, that I'm not going to provide any information, but you are going to search. And this another name is the blind search strategy. Once again, if I ask you that what is the blind search strategy, you would be telling me that the strategy is where no further information other than the linkage of these things is given to you. For example, this is the graph, and you are here and you want to reach it here. How to reach this particular point? Okay, so you are going to explore your frontier. You say that I can go in these two places. Then maybe you go into this particular direction. Then you see that two more directions are there. From there you explore something. So what is the order in which you can explore? should I go into and tell you that what is BFS and DFS? So there is one method called the best breadth first search. And breadth first search says that if here two paths are available, if you go into this particular direction, so you don't you go here, then you go here. Okay, one by one you are going to explore this. So anything that if the things are, for example, if I create the tree into this particular way, BFS says that first you evaluate this, then 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 this, like that. Okay. And another search method is called the depth first search. It says that you when you see this, then you go here, then you go here, you go depth first, and then you come back here, then you evaluate this one. Then similarly, DFS and BFS are into this particular way. So essentially, it becomes like this. It becomes something like this, that when everything is been evaluated, then you come here and then you start exploring into this particular way. In the BFS, you go into this particular direction. I would not go into the much detail. This algorithm is written and directly copied from a book called Corman. All of you know that. Corman is a book for algorithms. Very interesting book. You must read this book. And you must have already read, you have very big experience into this particular area. So this is the algorithm for BFS. If you have any confusion, please let me know. I can explain this algorithm to you, but I don't want to waste your time because I know that all of you are good programmers. So you know what is BFS. I don't want to waste your time. Only relevant part I am going to explain. Okay. Another blind search strategy where blind search means no information. Whenever you are on any particular node, no information is given to you apart from the what is the link. What are the other links? This information is definitely available to you. What are the links? So no other information is given to you. Then it is called the blind search strategy. Next blind search strategy is DFS, depth first search. Okay, here what you do, that one by one you are going to find out all the nodes in your vicinity, and then you call this particular routine that actually does that. Inside it actually goes and try to explore whatever things are actually possible and can be explored. I would not go into this detail, assuming that it is not needed and you know all these things. Everybody please say yes if you are agreeing with me that I need not to go in detail and tell you that what is DFS, BFS, but I suggest you that please once again revisit that how to find out the node. So these strategies are different. Is it fine, everybody? Should I continue?
Yes, yes, sir.
Yeah, okay. DFS, BFS is fine. Okay, so we were talking about uninformed or the blind search strategies. Once again, I would ask you this question: what is a blind search strategy? And you would tell me DFS and BFS. Okay, BFS generates best. BFS generates order of B to the power D nodes. What is B? What is D? Okay. So let's assume that I told you that whenever you have a graph and you want to search on that, when you have a graph is actually set of vertices and edges. Everybody, whenever I ask you that what is a graph, you say that it is a set of it is a structure that contains two sets, and one set contains vertices, another set contains edges. Edges means it's an ordered pair that tells that from which node to which node there is a link. So if I have a graph, I can convert it to the tree. Okay, on this tree, if I pick any node, so what is the branching factor? So branching factor means that how many things are going out. So they are not fixed, but I can tell that whether it is very large number or small number. If I say that B is the branching factor, what is the branching factor? If I say B is the branching factor, and you go to the D depth to search this particular item. So how many items would be actually explored? B to the power D. What would be the order of their exploration? This. This would be the order. BFS. Okay. One more thing, BFS maintains the things into, if you want to do the BFS, so you use a queue data structure. Whenever you want to do into DFS, you use a data structure called stack, because last item is most important. So whenever you put it, the next time that item is only going to come out for you. Okay. ये थोड़ा सा there is a states, okay, just small typo. Okay, next kind of search is called the informed search. That is a very important thing, and this is the subject matter of our main course. Okay, heuristic search techniques, and they are informed search. What do I mean by informed search? That when you are into this particular node, at that time some more information is also available to you. Okay, and using the more information that is available to you, for example, if I just wanted to tell you this. For example, you are onto this particular state. These are the three states which are the next state. Okay, so some more information is available to you. By this, what you can do, you can arrange them. You can tell that looks like that this has a merit of 20, this has a merit of 50, this has merit of 32. Okay, this has a merit of 50. So who is more better? Who is more better? Depends upon that. How can you use this number? If the goodness, if 50 says goodness, then this is the better one. Okay, so available choices were 20, 50, 32, three nodes. Earlier, what was there? That I had three nodes. Then you apply DFS or BFS. If more information is given to you, that goodness of this is 20, goodness of this is 50, goodness of this is 32, so you would go into this particular direction. Yes or no? You go into this particular direction. If you can do any kind of ordering using this information, using extra information, then you can tell that one is more promising than other. And this is important. Then you would not go into exploring this one, you would go into this particular direction. And this is called the heuristic search. Make sense? Definitely, these things are going to have more memory requirements and time taken, and based on that only we define that which particular strategy we are going to use next. Any questions on that?
So compared to compared to uninformed search, informed search would be having less memory requirement, right? Because for example, like in the search.
Okay, understand. Okay, understand. We would come back to this later. Actually, you are talking about the memory requirement while running the things. Okay, while running the things. Okay, another thing is that how much memory requirement is needed when I represent this thing. And again, there are various methods to optimize this. Okay, so directly we cannot tell this thing. However, in terms of the representation, just think in terms of the representation here, only node linkage information is available. Here, along with the node linkage, more information is also there. So that's why they have some more information. Okay, representation is a different thing, but there could be definitely different way to represent. So I need not to call you using your name. Now your name has a 10 characters, but I can tell you roll number 5 come. And you know that integer can be represented in only two bytes only. So why should I use your name? Roll number 5, roll number 6, roll number 10. So representation can be different thing. Okay, I don't want to go to that particular thing, but you see that the information available here and information you're here, if you just compare that, the information into the heuristic search would be larger. Yes.
Yes. I need to think on that.
No, information is involved. Nah, here, whatever information is there, that information is also here. Along with this, some more information is there by which you can do the ordering. So more information is there. Yes or no?
Yeah, possibly.
What's the problem?
Yeah.
But linkage information is there. Along with this information is also there. So it has more information. That's why it's informed search. Okay. All right, we have a map of Romania and we want to solve some kind of problem. We are going to see few more algorithms for you, and I request you to take the print screen of this particular screen. Okay, because later I would be asking you that what is the distance of between these things, and if this graph is with you, you can answer me efficiently. Okay, can you take it? Can you take the printout? Print screen. Okay. So this thing maybe we would be using at some point of time, and some other things we are also using. Take the printer screen. Okay, thank you. So let us start. This is the another algorithm that is called the uniform cast search, and this is the first time I'm going to be into the direction of AI. Okay, this is uniform cost search. This is another method that we are going to talk about today. So apart from the DFS and BFS, I'm going to talk about the uniform cost search. Okay. Uniform cost search, actually what it says that I have a frontier. In this frontier, so one thing I'm going to change here. Earlier what was happening, that into DFS and BFS, whenever there was a tree, if you want to go and find out something and search something, so when you are here, you find out this particular node, you test that whether this number is goal or not. Okay, goal is, if it is goal state, why should I explore more? Okay, but this time I'm going to change this, that when you explore something at that time, don't test that whether it is a goal state or not. You put it in a frontier. You put it into frontier. At the time when it is taking out from the frontier, at that time you test. At that time you test that whether it is a goal state or not. Once again, when the goal state, when you obtain any state, you put that state as it is inside the frontier. And when you take out from the frontier, at that time you test that whether it is a goal state or not. If it is a goal state, you return that I have find out this. Okay. So uniform search state says, the uniform cost search says that I am going to maintain a frontier, and this frontier is actually a sorted list. Sorted list. Sorted based on what? So there is some value I am going to put. Okay. Along with this, I am going to put a value. And yes. Okay. I am going to put a value. So what is that value? Okay. So into the old map. So in this old map, just consider this particular part. Okay, that I highlighted. Cebu, for let's assume that from Arad you reach to Cebu, and from there you want to reach to Bucharest. Okay, what path you should take? Okay, so this is what a scenario you have. Okay. So there are two places you can go. Figueres or Pelsia. These are two places you can go. So the algorithm says that in your frontier, initially there was Cebu with the value what? Whatever value here. Whatever value was here. And initially, if you start by Cebu, you said 0. And 0 is the value that from where you started. And then algorithm says that I'm going to take out this value. I'm going to take out this value, and I find out two values, that Figueres with the value 99, and Velsia with the value 80. I'm going to put it here. Once again, this was a sorted list, so therefore Velsia 80 comes first and Figueres becomes 99. Okay. If the earlier values were also there, so if 3-4 values already maybe there, so they also participate into the sorting, and therefore you got this particular value. What is the next step? Next step is to take something out. This Velsia is going to be taken out, and from here you have only one way to go, PTST. So you put PTST over here with the value what? 80 plus 97, because 80 plus 97. 80 you have already gone through. 97 is this. So the total distance is going to be this thing. Now three values are there into your array. They are 99, and 80 plus 97 becomes how much? 177. So next time this Figueres is going to come out. This is going to be given to you. When this value comes out, it gives you what? 99 plus 211. This is the place. By this you can reach to Bucharest. So in your array, what is the place? PTST and Bucharest. And what is the value of Bucharest? It is, if you add 99 to this particular number, it becomes 30. Am I right? 310. 310. Okay, am I right? And two values are there. One earlier values was, what was this? 99. I think 80 plus 97 was there. The 177 and 99 was there. So figure has gone. So what was this value? This is 177. Okay. So there are two values right now in my frontier. One is the PTSD with the value of 117 and Bucharest with the value 310. Okay. These two values are there in my array. When I take it out, I put the Bucharest inside. And they would be sorted in this way only because Bucharest has 310, PTSD has 117. So what is going to be the next step? Next step is going to be that you are going to take PTSD out, and PTSD out gives you 117. And from here you get 101. It is 218. And this is the Bucharest. So you in this particular thing, you are going to put what? Bucharest 310 and Bucharest with 218. You are going to put into this particular way. This is going to be again sorted because this in the uniforms cost search, the minimum value is going to be taken out. So you are going to take out 218 as an output. And at the time when you are going to take out, at that time you are going to test if it is a goal state or not. You see it is goal state, you need not to go forward. You get a path to go to Bucharest with the 218 kilometers. However, what is the important thing? That even before that you have find out the path to Bucharest and it was 310 kilometers. But you have not considered this, you have find out the better path 218 because your array, your frontier was shorted. Make sense? What I changed? I changed earlier algorithms were using that whenever I'm going to put something into this particular array, before that it was tested that if it is a goal state, then I don't put it there. I reached to the goal, I've done, but here it is telling no, please wait. At the time when you are taking out, at that time you please test that it is if it is a goal state or not. In this example, you have seen that we have earlier discovered a path of the 310 kilometer, but because of this sorting and methodology, we were able to find out the path with the 218 kilometer. That is a better path. Make sense? Yes or no? Yes or no? Okay. So, so what is the time complexity of this thing, space and time complexity of this thing? Both is going to be something like that. So if what happens now, look from A to B, if you want to go, so you have to go something here, then here, then here, then here. Why I am going to, so here, and then here, and then here, okay, and then here, then here. So different kind of path length you are going to follow. Somewhere there is a larger path, somewhere there is a smaller path. So, so if I say that, okay, the smallest path is epsilon, of the length epsilon, okay, smallest path is of length epsilon, and the total path I don't know. Let's assume that the total path length is c asterisk, okay. So how can I define the complexity? I can define the complexity in the term that because complexities are defined in terms of the discrete numbers. So how many discrete steps I'm going to take? So the better way would be that if you define if you divide the c asterisk by oh, why I'm doing the multiple number of time. So if you divide c asterisk divide by epsilon, so by this you are going to get something that how many steps are there? Yes or no? Rough idea that how many steps are there, because this is the smallest one. So how many multiple of the smallest one are there? We can find out by this. So you can apply a lower on this, floor on this, and then applies add one because it may have some fractional part. So you add one to that. So these many number of things I'm going to explore. So if this is the depth, then you apply to the what is the B means what is the branching factor. You put it on the branching factor, this particular number. So order of this thing you are going to explore. Complexity of this particular algorithm is this. Make sense? Yes or no? Yes. Uniform sensors clear. Okay. Yes. Okay. Last thing that I wanted to tell today is very interesting one. Few minutes back, we had developed actually the idea of that thing also, that I told you that if you have a graph, you can convert it to the tree. And because in the searching you are going into the into terms of the tree, search can be represented in form of the tree. If it is a tree and you keep exploring the things, you are going to nowhere. If it is an infinite way, if it's an infinite depth thing, then you are going to reach hit to the bottom and you would not be able to come back there. So everybody, are you with me? No.
Yes, sir.
Nobody is. So what I wanted to tell, if I have a graph, I can represent it as a tree. Okay, search can be represented as a tree. Its search can be represented as a tree. It cannot be represented. My point was this, that its search can be represented as a tree. So if the search is represented in form of the tree, so let's assume that this is the tree. Okay, let's assume that this is the goal. This is the goal. But tree can be of the infinite depth. Tree can be of the infinite depth. Okay, so if you start by here, go into this particular one and keep going down, 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 down. So you would be not be able to reach to this particular place, because how can you reach this? You are gone. This is the reason that DFS is not considered to be a complete searching algorithm, because it may stuck. But if you have done the BFS, so BFS is going to into this particular direction. So after some time, at the time when there is the result is even if there are infinite depth, but it would try to find out that if the research if the result is the goal is here. But DFS would not. It would go inside and get trapped. Okay. So one solution is that depth limited search. One solution is a depth limited search. You say that, oh DFS, please don't go beyond this particular depth. I say that don't go beyond to this particular depth. I am going to say that this is the L depth. Don't go beyond the left L. If I apply this particular method, then DFS can also give me the solution. Earlier DFS was not going to give me the solution, but now DFS can also give me the solution. Yes or no? Assuming the solution is inside in this particular thing, we can find out the value of L. Yes.
So depth is a assumption, right?
Our assumption that my solution would be into this particular thing. Finding out the value of L is difficult. How to find out this? So there is another method, that is the next thing, that iterative deepening, that says that if you, since you don't know, so you start L with the value of 1, then you make it 2, then 3. If you don't get the answer, make it 4, 5, 6, something like that. You keep increasing like that. Okay. So but
so for
if
example, yeah,
if
I was saying like
if somehow my L is correct, then I would be able to find out the answer. Yeah, please go ahead. Ask the question.
Yeah, I was saying like, for example, the chess example that we had, right? So the level of the computer player would be the depth. Put the depth on it.
Exactly. That's why I was at that time telling that please remember this particular line that you are the question that you are asking. Very important question, because you know that the infinite depth, finding out the right move can take the infinite thing. Then you cannot give me any move. But if I say that consider only 10 depth, then you can at least find out that what is the best move, and you can tell me that go into this particular way. Yes. Okay. Space complexity and time complexity, b to the power L. Space is b multiplied by L. क्योंकि every time b multiplied by L, these many number of items I am going to have na. So the space complexity is this much only. Time I have to complete visit all of them, so b to the power L. But there is a huge problem that I don't know that what is the right value of L. So the solution is go for the iterative deepening deep search. Depth first search, iterative deepening DFS, in which I am going to increase this 1, 2, 3, 4, 5, 6. So I would tell you more about this in the next class. Let's stop at this particular point. Thank you very much for joining.